I am Mr. True. In this video, we're going to talk about something called implicit differentiation. What we have been doing all along is called explicit differentiation. Equations where y is in terms of x. That means it's like y equals sine of x, or y equals x squared plus 2x minus 5, or whatever. Y is alone, and it's equal to everything, blah, 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 with x's on the right. Are in explicit form. Well, some equations are very, very cumbersome to deal with in explicit form, or just downright basically impossible to get into explicit form. So for those problems, we're going to use implicit differentiation. What that means is we're going to, find the derivatives of both sides of the equation in respect to, usually in respect to x. And, when we get to the y, we'll just have to, deal with it like this. We have the derivative with respect to x of 4x cubed. Now, if I were to run through this using the general power rule, which is the combination of the power rule and the chain rule, we would do 3 times 4 is 12. Reduce that power by 1, so it would be 12x squared. And then if we had an inside function, and that inside function u, which in this case is x, now this is going to be a little extra to kind of explain what's going on. This is the derivative of 4x cubed. But if we were using the chain rule, it would be the 4 times 3 is 12, reduce the exponent by 1, here's the inside function of x, and then we need to find the derivative of the inside function, or it would be the derivative of x with respect to x. Well, dx over dx just cancels out to be 1. So we're always, doing this derivative with respect to x, but when we're derivating the variable x with respect to x, that cancels out and just simply becomes 1. Now, why am I bringing that up? Because in our next example, we have x and y terms. Now, these aren't full-blown equations, these are just expressions, but they're to show you, how you write the notation for implicit differentiation that we're going to use in the equations here coming up. So the derivative of 3x squared plus y cubed, that's just two terms, and we know that we can find the derivative of each term and then add them together. So this is going to be general power rule, and the constant rule. 3 times 2 is 6. Reduce the exponent by 1, so just 6x to the 1 power. We don't need to really write that. Power rule here as well. 3 times 1, which is in front of the y, so 3y. Reduce the exponent by 1, so there's 2. And keep it in the idea of chain rule, we have to do the derivative, we have to show the derivative of y with respect to x. Now, when we did all of our explicit form problems, all of our explicit differentiation, you did not ever really see me write this. I mean, I did write it a couple of times, but normally I would just write y prime or f prime of x and said, it's the same as the derivative of y. So we can do the same thing here and write this as 6x plus 3y squared, and just write that y prime notation again. But it is the derivative of y with respect to x, in this example anyway. Here we have 3x squared times y cubed. It's not plus, so we do not have two terms, we have one, so we're going to have to use the product rule. So the product rule says that it is the first factor, 3x squared, times the derivative of the second factor. So we're going to find the derivative with respect to x of y cubed plus, now the derivative of the first factor, so derivative with respect to x of 3x squared times the second factor, which is going to be y cubed. Okay, so chain rule here, we got the y, so we're going to have a little y prime thing going on there. We have 3x squared, 3 times 1, so 3y, bring that power down by 1, 2, and then again, the derivative of y with respect to x is not going to just cancel out, so we have a y prime there, or derivative of y over derivative with respect to y, or of y with respect to x. 3 times 2 is 6, so we have plus 6x, and then y cubed. So here we have 3 examples. This is the answer right here. Well, I can do 3 times 3 is 9. So 9 x squared y prime plus 6xy cubed. So we have 3 examples of finding the derivative of just an expression using implicit differentiation. Now let's move on to our first example. Well, we're going to give you the rules first. The rules or guidelines for implicit differentiation. The next example is going to be a long one, but I want you to see why we want to learn about implicit differentiation and why we don't want to just stick with the explicit form. So we're going to have pretty long of an example comparing explicit differentiation with implicit, and then ultimately show you that you really do ultimately get the same answer. And probably end the video with that, and then do another video of just examples of implicit differentiation. I'm Mr. Tarrou. I'll be back in a second with my remote and that example. Bam! Here are 3 steps that we're going to work through as we go through our examples in this video and the next. We want to differentiate both sides of the equation with respect to x. We want to move all the terms with dy over dx or y prime to one side and all the other terms to the other side. If need be, we're going to factor that dy over dx or that y prime out of all the terms. I would put them on the left-hand side and then simply solve for y prime. Those are the steps. Let's see what the work looks like. Now, when we get to the next step, my first example, I am going to do it explicitly, and then we're going to look at it in the implicit method and go, wow, that was a lot quicker. Anyway, so here we go. Our one fairly simple, innocent-looking example that is going to really push the idea through that we want to, in some cases, do implicit differentiation over explicit. We're using this because we can do explicit differentiation, unlike some of the questions you'll have in this homework for this section. But it will be more difficult using the explicit method. Now, hopefully you recognize what's going on here. This is x squared plus 9y squared equals 9. When you have 2 squared terms, an x squared term and a y squared term, and their leading coefficients have the same sign but different leading coefficients, we have 1 and 9, you have an ellipse. If I take this, and I need a lot of room to show my work, so just think, if we take this entire equation and we divide it by 9, we're going to have x squared over 9 plus y squared over 1 equals 1. That's a standard form of an ellipse whose major axis is horizontal. This ellipse is centered around the origin. We'll move left and right 3 units, up and down 1 unit, and get an ellipse that looks something like that. That's the greatest drawing, but whatever. So that's what we're going to find the derivative of. Well, that means we have to get y alone. So we're going to subtract both sides of x squared, get 9y squared equals 9 minus x squared. Divide everything by 9. So divide by 9, divide by 9, divide by 9. We'll get y squared equals 1 minus 1/9 x squared. Square root both sides. Whenever you introduce your own even root, don't forget to account for both the positive and the negative answer. This is going to be negative plus or minus the square root of 1 minus 1/9 x squared. I do realize both of these terms are perfect squares, by the way, but you cannot square root, and get like an answer. Like square root of 4 plus 9 is not 2 plus 3. They don't care if these are both perfect squares. It's 2 terms. You cannot just square root them. This, if you want to know the domain of this function, if you're concerned about that in a particular question you're looking at, you can take what's inside the square root symbol and make sure that it remains greater than or equal to 0. I'm going to get off course here a little bit and finish this derivative in a second. I can subtract both sides by 1, get negative 1/9 x squared is greater than or equal to 1, negative 1. Divide both sides by multiply both sides by negative 9. I'm just going to show it once. Negative 9 times, or divided by negative 9 is positive 1, so we have x squared. We're multiplying both sides of the inequality by a negative number, so we're going to change the direction of that inequality. And now we need to square root both sides of the inequality to get our 2 answers. Well, when you square root, when you're working with an even root symbol on an inequality, you will have to change the direction of the sign for the negative answer. So when you square root both sides, we're going to get that x is less than or equal to 3 and x is greater than or equal to negative 3. So the domain of this function is all x's between, let's use interval notation, between negative 3 excuse me, and positive 3. Back to the finding the derivative. So I want to find y prime. So I'm going to rewrite this because I don't like using radicals. So y is equal to plus or minus 1 minus 1/9 x squared to the 1/2 power. So we're going to have to use the general power rule or the chain rule with power. So we're going to have y is equal to plus or minus 1/2 times 1 minus 1/9 x squared. Reduce that by 1. 1 over 2 minus 1 is, negative or negative 1/2. Because you need a common denominator. Okay, so that's I just found the derivative of the outside function, the square root function or the power of 1/2. Now I have to, do the chain rule and find the derivative of the inside function or the derivative of u. So that is going to be, let's see, derivative of a constant is 0. And we have 2 times 1/9, so negative 2 over 9 x, and reduce that power by 1. So this is my u, and this is my derivative of u. We need to clean this up. Again, I forgot my y prime mark there. We need to clean this up. So this can be rewritten as y prime is equal to plus or minus 1 over 2. I want to write this so that I'm kind of overdoing this work here, but I want to show that this has, I want to get rid of that negative exponent, so that's really 1 over 1 minus 1/9 x squared to the, well, let's go ahead and put that square root symbol around it. Why not? So 1 over the square root of 1 minus 1/9 x squared times negative 2 over 9. And just to make sure we understand where all the variables need to be, that's 2/9 times x, or 2/9 times x over 1. So it's negative 2x over 9. Now, canceling stuff out here, we have the 2's are going to cancel out, and that's pretty much it. We also need to take into account, normally we just write plus minus and don't think about the order that they're written in front of a square root symbol, but it does matter. It certainly is going to matter in some of your calculus work. So when we take this negative x and multiply it by 1 and then multiply it by plus minus 1, it's going to change the order of that plus minus. So this is going to be negative plus, let's see, 1 and 1 and x, so x over 9 times the square root of 1 minus 1/9 x squared. Now this would be done. I mean, we would be happy with this as our derivative if we were doing it explicitly. And we're going to have to finagle this a little bit in a second, because what we're about to do is how we're going to differentiate x squared plus 9y squared equals 9 implicitly, but the answer is not going to look the same. So I'm going to have to finagle this a little bit to make sure that you understand that they are the same equation, equivalently the same equation. So let's pick a different colored chalk just to highlight we're doing implicit. Pull that original function back over here, x squared plus 9y squared equals 9. I did a little of extra talking here because I wanted you to see the function and understand its domain, but all the stuff in white so far is finding the derivative explicitly. Now we're going to do it implicitly. We're going to find the derivative of both sides of the equation with respect to x. So when we have an x, it's going to look like always. The derivative of x squared is 2x. Excuse me. The derivative of 9y squared, power rule again. So 2 times 9 is 18. Y, because we reduced that exponent by 1, but now I got to write that extra notation that I'm not finding the derivative with respect to y, I'm doing it with respect to x. So I need to add in another y prime, or dy over dx. It's just quicker to write. Equals, excuse me, the derivative of a constant is equal to 0. I need to solve this for y. So I'm going to move the 2x over the other side. We have 18y, y prime equals 2x, divide both sides by 18y. And y prime is equal to 2 over 18 reduces to 1/9. So we just simply have x over 9y. Let me just make sure. I feel like I might have made a mistake somewhere. Oh, yes, I did. That's a positive 2x, and I need to subtract it over the other side. I forgot that negative sign. There we go. So we have y prime equals negative y, or negative x over 9y. Those do not look the same. Hello? I like you told me you're going to get the same answer, because, well, first of all, that's a lot less work, but if I don't get equivalent answers, okay, here's the deal. This is y in terms of x. This is y prime, that's y prime, but I have an x and a y variable in the function. So if I can take this and manipulate it a little bit so I can do a substitution with the original problem down here, well, not quite the original problem, but right here, I want to use this in, let's see, if I have not used a color yet, yellow. I want to use this as some type of substitution into this function to make this look like that and prove to you that you get the same answer. Well, this is y equals plus or minus the square root of 1 minus blah, blah, blah. This is a perfect match, almost. This has a plus or minus in front of it, though, and this has a 9. So, and also, I have a plus or minus, but it's on top, but it's backwards. It's negative positive. You wouldn't think that would make a difference, but it does. So what we're going to do is, you do know that, say, like negative 2/3 is the same as negative 2/3, which is the same as 2 over, all these are the same fraction. Those all are negative 2/3. It doesn't matter where the negative sign is, top, middle, or bottom. So I'm going to move this negative positive that's with the x to the bottom of the fraction. Now, negative 2 times 3 is 6, and 2 times negative 3 is also negative 6, right? I did say negative 6 up here. So when you're doing multiplication and one of the factors are negative, it really doesn't matter which one of those factors is negative, you're still going to get the same answer, the same product. So now what I'm going to do is make this look, I'm doing those in tiny little steps. I hope this is making sense and I'm not going on too long for you. This is going to be x over, instead of having the negative positive on the 9, I would like to have it 9 times negative positive square root of 1 minus 1/9 x squared. So I'm getting the positive negative closer to the radical, so you're going to be able to see the substitution I'm about to do, but it's not exactly the same. So what we're going to have to do to make this substitution happen is multiply the numerator and the denominator by negative 1. Negative 1 divided by negative 1 is 1, so I'm not changing its value, I'm just changing the way it looks. So that is equal to negative x over 9 times plus minus the square root of 1 minus 1/9 x squared, and that can now be taken out and substituted in with y, and guess what's about to happen? I'm about to get excited because I have exactly the same answer as I got with the implicit differentiation. All of this work is the same as that. So hello, we would prefer to do implicit differentiation when needed. Now, I'm going to go ahead and erase this board a little bit. We're going to use this information over here in orange to find some questions about slope. I mean, we find first derivatives to find the slope of the curve at a given point. We can see there's going to not much of a difference, but a slight difference. When we find the derivative value, when we want to find the slope at a given point, the slope of this along this ellipse at any point that's within its domain, I need an x and a y value. So all other questions so far in our textbook that have asked you to find the slope of a curve has only needed to give you the x coordinate. What if they only give you the x coordinate? Or most of the time they will give you both the x and y coordinate, the entire point, so you can find the slope of that curve at that point. So there you go. Implicit compared to explicit differentiation, even when it is possible. Here's the 3 examples we're going to do for slope and call this video done. we have that ellipse, remember, and it is nice to have a sketch of the function if you can, or are willing to take the time. That way you can see the reasonableness of your answers. Now, this ellipse is centered around the origin, and I'm asking for the slope at 0. Now, whether it's at 0, 1 or 0, negative 1. It should be a slope of 0 because it maxes out or bottoms out of those values. So let's just make sure. So we're going to take our white chalk here, slope at 0. So y prime at 0, let's see. It's negative x or negative 0 over 9 times y. Well, you know, I worked the problem both ways, so I know what y is. If I did not, they would need to give me the y value, or I would need to, you know, take this and solve it for y, which I did, and then of course erase. So y is going to be equal to plus or minus the square root of 1 minus 1/9. I just rather read up my notes and not make a mistake. 1 minus 1/9 x, where x is equal to 0. So let's see what we have here. Oh, why do we need to work this out at all? I mean, this is 0, 0 squared is 0, 0 times 1/9 is 0, the square root of 1 is, but who cares? The numerator is equal to 0. When the numerator of a fraction is equal to 0, that entire fraction is equal to 0. So thus, yes, we did get what we expected. Y prime at 0, the derivative at 0, is equal to 0. Now what about at 3? Well, that's going to be y prime is equal to negative 3, negative x, over 9 times, and again that's going to be, why did I erase that y value? I don't want to make a mistake here. So y is the plus or minus the square root of 1 minus 1/9 times x squared, or x value is 3. So let's see what's going on here. We have 3 squared, which is 9. So I'm going to take that out. 3 squared is equal to 9. 9 times 1/9 is equal to 1. 1 minus 1 is 0. The square root of 0 is 0, so that's all. 0 times 9 is 0. So now my first example had 0 in the numerator. That was great, but now this is working out to have 0 in the denominator. That shouldn't be shocking. That's why we have a picture. That point at 3 is the rightmost point of the ellipse. It's the end of the major axis. It's where the graph starts to curve around. The tangent line at that point is indeed vertical. Vertical lines have a, sorry for the interruption there. So we shouldn't be disturbed because vertical lines have a slope that's undefined. And so thus our derivative should be coming up with us trying to divide by 0, which we do know, of course, is undefined. So good, we got the answers we were expecting based off of our graph of the function using our derivative here. Then at 1 comma 2 square root of 2 over 3, so we're over a little bit, the graph is starting to fall, just some. I gave us a specific point, so I don't want the slope here and the one down here at the bottom. I just want it at 1 comma 2 square root of 2 over 3. So, I got an x, I got a y, I got a derivative function, so y prime is equal to negative 1 over 9 times 2 square root of 2 over 3. 9 divided by 3 is equal to 3, and 3 times 2 is equal to 6, so we have negative 1 over 6 square root of 2. If you'd like, you could rationalize this and get negative square root of 2 over square root of 2 times square root of 2 is 2 times 6, which is equal to 12. Let's make sure I have not made a small mistake. And no, we're good. So, I'm Mr. True. If you'd like to see a lot of examples of doing implicit differentiation, please watch my next video, but I think for now we're good with the introduction to implicit and understanding why we prefer this method. I'm Mr. True. Bye! Go do your homework!